Hi, and welcome back to my physics online video lecture series. Today's video, we're going to be talking a bit about the Young's double slit experiment and the optical interference that came from it. So this was a very famous experiment conducted kind of at the turn of the century, 19th century, so early 1800s, by Thomas Young. And one of the key sort of conclusions that came out of this experiment and held sway for the next 100 years or so is that light is a wave. Okay, so one key conclusion, light is a wave. It would be basically a little more than 100 years from that experiment before other results started to suggest that light might also in fact be a particle. Okay, and that was a debate that had been raging for actually kind of hundreds of years. Isaac Newton and Christian Huygens were two of the early proponents of those two sides. Specifically, Huygens said light is a wave and should be modeled as a wave. Newton said light is a particle and should be treated and modeled as a particle. And so this was sort of the first that I know of experiment that really was able to test those two claims, and it came down very strongly actually on Huygens' side, that it's a wave, and against Newton's assessment that it was a particle. And it wasn't until the photoelectric effect, which was described by Einstein but observed by others, that we started to realize that, you know what, maybe Newton was also right. Maybe, in fact, light is also a particle. So today I want to talk a bit about this Young's double slit experiment. And so let's get into that. What is it that the double slit experiment consists of? So let's pull up our little drawing pad here. Essentially, in the double slit experiment, you have a basically you could call it like a slit mask, or essentially you have some barrier which is opaque. So these regions right here represent opaque. And then you have light incident on the slit. So I'm going to represent my light as a series of wave fronts. And these wave fronts are meant to be plane waves. So essentially that means that you have the same intensity or brightness here as here as here as here as here, etc. It's not focusing, it's not defocusing. And these are moving towards the slits in this direction. I should note that this is not meant to be to scale, by the way, because the way I've drawn it, the wavelength would be the distance from here to here. One of the requirements for this double slit experiment is that the wavelength needs to be less than the slit separation distance. For what it's worth, that slit separation distance we're going to mark out in this light blue color, basically is from center of slit to center of slit, and we usually denote that with a letter D for distance. So that's your separation distance. Okay, and then when the light hits these slits, it basically passes through them, and it only really can pass through this area here and this area here. So these two slits allow light to essentially like leave from the slits. And so let's actually give it another wavefront just to be kind of overly pedantic about it. light now leaves these slits as a series of wavefronts like this, it propagates in all directions. That effect, by the way, is called diffraction, and we'll study it in a different video. Okay, now let's say that the light is allowed to diffract for a very large distance. And by very large distance, what I really mean is we allow them to diffract for a distance that is greater than the slit separation distance by at least an order of magnitude, and probably more. And remember again that the slit separation is larger than the wavelength. Okay, so if I come back here and label some distances, this distance right here, whoops, that's a little thicker than I wanted it. This distance right here would be kind of representative of one wavelength, lambda, for our light. Okay, we allow these to propagate, and I'm just going to do like a little ellipsis here, and I'll redraw this diagram on another slide. After a long propagation distance, we put somewhere over here a screen or some other detector that we can project the light onto. And what we end up seeing on this screen is, well, before I answer it, maybe I should ask, what do you think we see? What do you think we see over here? We have two light sources. So, you know, there's some possibilities. We might see on the screen two lights. These slits, by the way, if you look at them in like face on, they're usually like really long and really narrow. So if you're thinking of them as being like a spotlight, then you'd expect to see a couple of really long, really narrow, bright lines on the screen, and then more or less dark everywhere else. So that's one possibility. Another possibility is, you know, you may be looking at these and saying, okay, well, I see that this right here kind of is spreading out. So maybe instead of two long, thin, maybe we get two broad, bright areas, or maybe it washes out, and so it's, you know, fairly well lit over a certain area, like maybe from here to here, and then dark thereafter. And then another possibility is maybe we just see a bunch of bright lines and dark areas in between. So instead of two bright lines, maybe we see a whole bunch. So think about that for a minute. Pause, and then when you have an answer, hit play, and I'll reveal my answer. Okay, so the answer is that you actually see a series of bright and dark stripes on the wall or on the screen. So essentially, I'm going to draw this a little thicker. You'd get like a bright spot here, and then you'd have a dark, and you'd have another bright spot here, you'd have a dark, you'd have another bright spot here, you have a dark, another bright one here, a dark, bright one here. And so essentially my red lines represent bright, and then this space between them represents dark. And again, if I should note that I'm not trying to draw this thing to scale. If we make this distance from slit to screen L, the main requirement for the analysis we're doing, this is what's called Fraunhofer analysis. The main requirement is that L be much greater than D, and D be greater than lambda. Usually it's much greater. So here, for example, a typical value might be that you place this screen, so e.g. L is 30 centimeters, that's roughly 1 foot. D might be, say, 0.125 millimeters, That's one of the standard values that you can get if you buy like the Pasco double slit screen. I'm sure Vernier and some others have similar distances. And then lambda, you're using a laser pointer. If it's red, lambda is probably for a laser pointer 650 nanometers. If it's a helium neon laser, then it's 632.8 nanometers. If it's a green laser pointer, it's probably either 532 or 515, etc. All right, and so I'm showing here actually a picture that I took using a red laser and using a slit separation. I don't remember if this was 0.125, 0.25, something like that. And I think that the distance from the slit to the screen was about a meter. The wavelength of the light, you can see, is kind of reddish, at least on the parts that are not saturating my camera, is actually 650 nanometers. So this right here is the pattern that I got on a screen. The screen was basically like a piece of, like I have a notepad like this one right here, and I was using basically like the back of it as my screen to project onto, because it was rigid enough to stand up without needing to be really secured in place. Probably would look a little nicer on a piece of white paper, but you can see the pattern very nicely here. So now the question becomes, why does it do that? And I'm not going to answer all of that. I'm not going to answer like what the pattern itself is described as in this video because of time constraints. But why does it do this? The answer is because light traveling from one of these points as opposed to the other is going through different path lengths. So let's go ahead and duplicate this slide so I can add some more drawing to it. If I were to draw a line, and this is meant to be more or less a straight line, if I draw a line from here to, say, this point on the screen, and I draw a line from here to the same point on the screen, you can look and see that those two lines have different lengths. So light had to travel a little farther here than it did here. So why does that matter? Well, initially these 2 points are what we would say is in phase. They have the same phase, they are coherent with each other. If I was going to use an equation to describe them as an electromagnetic wave, which we'll get to in a different video, it would be the exact same equation at this point and at this point. But because they're going through different path differences, different path lengths, they each pick up a different amount of phase. What I have here is a little plot in which I have a blue line and a red line and a green line. And basically the blue line and the red line represents like the wave at, let's say, some arbitrary point on the screen from the top and from the bottom. So we could, for example, mark off this top one as blue. Even though they're both actually red light, we could mark this one as the blue, bottom one as the red. And the green represents adding the two together at that point. And so the taller the green, the brighter the light at that point. And I can change the phase difference between them. Zero phase difference means essentially they have the same path length. So the phase difference is given by the delta phi is 2 pi delta x over lambda, where delta x is how much farther one of these had to travel than the other. So if they travel the same distance, then delta phi would be 0. So go back to this little plot. 0 path length difference results in this green. But what happens if I make the path length difference, say, like 1 pi? Then they are exactly out of phase. Peak of the red and peak of the blue are out of phase. Peak and trough line up. You add together, you get green. That's a dark spot. And for some path lengths, you get bright spots and some dark spots and some something in between. So in between is like, so If it's in between, then it's needed bright.